Hey everybody, how are we doing? Thacker, good to see you. Is it possible to go over part 5, task 2 for assignment 8? You bet. Just saying that in the chat there. Let me get it up and going. Just getting everything ready around here. Gosh, so many things. Whew, I tell you. I'm gonna have my second cup of coffee here in a little bit, but wow, it's just everything is so busy. How does everyone feel about their semester right now? Because wow, I just sometimes this semester, like, I'm like, wait, it just started, and I'm like, no, it's we're like 70, 75% over right now, and it just wow. I don't know. That's I can't believe it. Tomorrow's Good Friday, spring recess. I just it just I don't know. Before you know it, the whole semester. It is just a blur. I don't know if you feel that way, but that it just gosh. Like I must stop just being like, oh my gosh, we are so far into the semester. Let's do this. Let's hop into this. Here we are. We got everything going on. Let's put in a random student ID. Oh, we don't have to do it this time. I made it so you didn't have to do it. Yay! We're using the full data set. This is part 5 for task 2. Okay. So let's get on here and talk about part 5 for task 2. Extrapolation explained with numeric backing. So extrapolation is when you go outside the x bounds of the model. So let's look at some extrapolation right here. What we need to do is we need to build a model first. And I'm using a totally different model than your model because I like to do pretty much different data sets than the ones we're using. So I'm going to use a totally different model right here. I'm going to predict body fat using, we need the tilde, weight, let's go height. Can we do age? Are these included? We need to first add in the data frame. Data frame equals body fat. Let's find out. They are included. And let's go ahead and let's first visualize the model here. We don't need to do these things for this part. I know, right? Oh, congratulations on that, Thacker. Awesome to hear that. That's really awesome, man. Is this the same data set? That looks to be... Oh, because I've got it saved. Oh, did the save set... Body fat not found. Wait, what? Let's look right here. That's why it didn't work. Body fat. Am I going crazy? Okay, now it ran. Okay. Well, we can't visualize the model then. The reason we can't visualize this model, and is that not running? Okay, that is running. Let's make a summary of our model. It's a multivariate model. My brain's still turning on right now. There we go. We got height, weight, we got age, multivariate model. What we can do is we can run the we can run the influence plot. Let's look at an influence plot on this. We don't want this to be right there. That'll break it. There's the influence. Let's look at the influence plot. And there, whoa, ho, what we got right here. Awesome. Yep, we're doing Thacker's question, you bet. We're doing some extrapolation right here, and look at this. We've got a point right here, we got a point right here, and we got a point right here. Do we have 3 points? We have 2. So these are the high influence points right here, like this point right here, this point right here. These row number 39, row number 42 are super high influence. And I'm only looking at these characteristics right here, body fat, height, weight, age, and height. Now, when you look at influence, influence only deals with which variables? And we're going to do the extrapolation right here, Thacker, you bet. So influence and extrapolation are kind of similar topics because they only deal with the what. Influence and extrapolation only deal with the what variable. Hint, this one down here. I mean, it's not on this axis right now because this is leverage, but influence, or excuse me, my brain is breaking this morning. Leverage and extrapolation, which leverage is a part of influence. Leverage is 1/2 of the components. There's the other component right there for influence. So what variable does leverage and extrapolation deal with? Extrapolation's a good way. You got it, Thacker. Great job. Let's throw out some points. Mubot, you're not even awake. Let's wake up Mubot right here. Were we gonna... Oh my gosh. Broke the whole stream. Mubot. World breaker, Mubot. Don't do that, Mubot. Don't crash the whole stream on us like that. Don't you do that. So we have the points right here. You can actually get the points. Mubot is awake. You can actually get the points by going down here and taking the leverage. So you can actually store them right here, and you could go here to rows and put them right here, and then you could go to your data frame and take those rows you're interested in and look at them. Now, I don't want to look at all of the data for this. I'm just going to go 1 through 5 right here. So what we're looking at are the rows that appeared here, this one and this one. We want to look at the unusual nature of their X characteristics. I put in weight, height, and age. So I'm going to remove that fourth one right there. And let's remove the output. And this person, one of these two individuals, I don't know which is which right now. I guess it should be... Oh, yeah, sure. Thinking about some code right there. So we've got, I'm just want to figure out which one. Oh, well, it's obvious. This person over here is the person who weighs 363, and they have a height of 72. Oh, whoa. Maybe not. This person has a height of 29. That's probably a data misentry. This person reported a height of 29 inches and a weight. I seriously think that's got to be a data misentry. That's got to be like 69.5 or 59.5. Probably 69.5 considering they're 205. But they reported they're 29 inches tall. What we could do is we could go here and we could eliminate one of these individuals and we could see which one kind of goes away. Let's go here and eliminate row 39 just to see what the model looks like without them. And let's rerun the influence plot right here. And so row 39 is the closer one. So row 39 is the closer one. Oh, wow. So this is row 39 is this individual right here. Let's remake our plots. Just doing some data investigation before we do the influence. So that's 39 right there. This is the person right here. And this person is over here. So just doing a little bit of investigation. And I guess it would make more sense that you think about how unusual this person is, that they're 29.5 inches tall. That's 2 feet 6 inches. Probably a data misentry. At this point, I'd be kind of willing to throw it out. We don't really like to throw out data, but I don't know if I believe it. Actually, they're less than 2.5 feet tall. Probably a data misentry. I'd go out on a limb and I'd throw it out. If I was working with this data, I'd throw it out. I'd be like, I don't think, because then we see here 205 pounds. If somehow it was different, I don't know, it just doesn't make sense. And the body fat doesn't work either. Just mathematically, I don't think we're mathematically on par with that. Let's throw out some points. So let's look at the extrapolation check right here. Now, when we do extrapolation is a matter of degree. And if you think about when you'd be extrapolating, there's a few ways to look at this. So thinking about extrapolating, let's go here to body fat. Let's only look at the variables we're interested in. And frankly, we only need to look at the x's. So when would we be extrapolating on someone's age? When would we be extrapolating on someone's age? So extrapolation is the idea of going outside of your x or your x's. So when would we be extrapolating on age? Wow, that's pretty interesting. A little bit end interesting right there. When would we be extrapolating on age? Like just in the univariate sense. It's a multivariate sense. We have that graphic. I don't have it up right now. But extrapolation is a multivariate idea. Exactly. And that's just kind of the basic idea of it. If you go into the multivariate idea of extrapolation, which is much, especially in the three variable sense, would be very hard to understand. Like, let's take away age. And this is kind of what we're doing in class right here. It's very similar now. We're taking away age, and we're just going to look at height and weight, because we could talk about extrapolation like this on the x's. Let's call this model extrapolation. Model extrapolation, because we're going to use this model to just investigate some extrapolation. Because the idea of extrapolation is that we are outside the x space of our model. And so going outside the x space of our model, whoa, look at that. Just because of the craziness, because we got an extreme individual here. So the x space of our model looks like the following. Just because of, are they behind that? Let me find out where they're at. Yeah, they're behind that. Couldn't see them in the plot. They're blocked. So the majority, this is for task 2. Yep. It's the very end of task 2. The majority of our data is over here. You've got this ridiculous point over here. I truthfully think this is some sort of misentry of data. But this is the cloud of your data right here. This is kind of the X space of your model. This isn't X being explained by, or we're explaining our X's with our X's. And so this is the X space of the model. And so right in here, right about here, maybe a little over here because of the outlier, but this is the what of the X's somewhere in here. This is the what of the X's somewhere in here. Like what is this of the X's? And actually, what are they? They're row, I'm going to remove them for a second. 42. I think they're 42. To make a better understanding of this, there we go. Right about in here, what do you have? Without that extreme point, where are we at? The mean of the X's, exactly. So this is the mean of height, this is the mean of weight, and this is the mean of the X's. So the way extrapolation works, in the X's, and you might be saying, but Brian, this is a Y. But this is a multivariate X space. So we're using our X right now to explain an X. We're just doing two X's because it's really hard to think about extrapolation when you get into like, it literally, Kayla, goes into eigenvectors and eigenvalues, and you're thinking about like dimension reduction. It's crazy. Yeah, when you think about it in like the multivariate sense. Where we'd be extrapolating the least, if you think about how extrapolation works, it would start to radiate outward. Like as you go further and further out, you're extrapolating more and more. And it's gonna go by an eigenvector sort of way right here. Like you would create the orthogonal space and create this sort of eigenvector space to where we can put everything on an even playing field. We don't need to go into too many specifics on it, like great details, but it should be known that the further out you're going in this kind of multidimensional cloud, which is going to depend on how many variables you have, the more you're extrapolating. So by the time you get out here, you're extrapolating a whole bunch. Like, and then if you leave the X space, but does that kind of make sense? In football terms, would it be unusual for a team to get maybe 200 passing yards a game? So you have to think about, like, it might not be unusual for a team to get 200 passing yards, but if they get 200 passing yards and they get 0 running yards, that might be unusual. Like, we have to think about unusual combinations. So, like, it's not just, you can leave, like, this point, if you put a point right here, let's put a point right here, all of a sudden that is very unusual, but when you move it over here, it's not so unusual. So, and I'd have to move it orthogonally, but the combination is what makes stuff odd. Like if you have 10 fumbles, but you could have the amount of yard lossage that you would expect with that. So I'm trying to think of like football terms. Sometimes I'm not the best at sports examples. Hey, Lizzie, good to see you here. Ask any questions you have. So the way I want people to kind of think about this question right here with extrapolation is when you do extrapolation, we don't need this code technically. That code's super important. When you do extrapolation, as Kayla was pointing out, you're leaving your X space. You're leaving, you'd be predicting for things. Generally speaking, unusual combinations are hard to think about because you have to think about the multivariate combinations. But the easiest way to think about extrapolation is to think about just leaving the X space. But you could do an extrapolation check right here, and you can check anything, and you can find something that's far out. If you just create a data frame, and this is one way to like show something would be an extrapolation. And let's just go here and pick weight. We're going to do weight is equal to 110, and we can do height is equal to, let's say, here we'll go to 80. And both of these are outside the model. We'll go to extrapolation check. We'll go to our model, and we'll go to new data equals df, and it should work. And this is in the 99.2nd percentile. It's actually not outside the bounds of our model, interestingly enough. Yeah, I guess somehow that combination is just at the edge boundary of the relationship that exists. I might not have saved the new model yet, or I might have the original model that has that extreme point. And I think the extreme point is the 1 point, and that kind of makes sense. How many data points does this have? 222. That's about on track. It's like 1 point or so. Do not want to interrupt, but you, yeah, of course. Yeah. About the screening, you bet. We can do that here next. So this is at the edge of the outer cloud. Does that make sense? This individual right here, does it make sense what this is telling you right here? This is in the 92nd percentile of like as you go outer cloud on this data. So for task 2, do we need to do that code to find out how far it is from the data? I would maybe do it. I mean, it's good. This is going to be on the take-home final. So this is one of the questions that is on the take-home final. So understanding how to use the code, having it in an assignment where you can reference it and be like, oh yeah, I wrote that. That's how that works. That'd be a good thing to do. The summary can help us understand where we are extrapolating. So the summary can be used to be like, okay, we are extrapolating outside of these bounds, generally speaking, but it can be for unusual combinations too. Like this person, yeah, I'm surprised that, yeah, it's because of our extreme outliers. That should be, oh, we still have 1 point that is further out than this. 1 point that is more unusual. Wow. It's because of the ridiculous point. It's because there's like 2 points apparently. If you think about 99.6%, so if we divide by, yeah, because there's like 250 points. So there we go. And so there, when you saw this right here, there was 1 point that was more extreme. And then right here, there was 2 points that were more extreme. Does that make sense with this? And why am I figuring out this way? Well, if there's 1 point that's more extreme, then 251 of the 252 points are within it. And that's what this code is telling us when we see this right here. That so does this make sense, Roderick and Kayla, what this code is telling you specifically when you see 99.6? It's like if you do a multi-dimensional cloud of data, whatever point you're talking about, when you go out in the multi-dimensional space, the percent of points that are like within that cloud is 99.6. So you would be at the edge of that cloud at 99.6. If you're at the mean of the data, you'll get 0. So you can just go here and take the means and put them in. And if you put the mean for height and weight, when you do extrapolation check, you'll get 0, which means if you think about this, like theoretically speaking, we're right here at the center of this X space. So when you get 0, you're right there at the center of the X space. And as you get higher and higher numbers, you're going further and further out in the X space, like a multi-dimensional cloud. Does that help with the Thacker, Kayla, and Roderick? Does that help with the understanding of extrapolation check and the idea of like, it gets confusing when you think about leaving a multi-dimensional X space. I think that's where it's like, wait, we're dealing with 2 X's right now? Yeah, it's I just wonder, yeah, exactly. So with the percentiles, I think that makes it easier because the 0 percentile is right here at the mean of the X's. So whenever you see 0 percentile for the check, where is it? There we go. When you ever see, yep. So the 0 percentile is right here, and then it's an orthogonal space, like which means 90-degree angles. Everything is like, and then if you get to the it'd be a 3-dimensional orthogonal space where this one's coming at you and this one's doing this, and everything, yeah, eigenvectors and eigenvalues. It's so fun. The math behind it is super cool, but it's very hard to visualize, especially thinking about it. I could make some 3D plots of it. I won't do it today though, but I could make some 3D plots of what the space would look like. And then we want to know how far are we out in the cloud of the space? Like what percent have we left the X space? Because the X space is going to make some sort of like multi-dimensional thing that data frame we can exist in. Here was the question from Discord. Could you further explain what details to discuss about the leverage in general? Yeah, which one is that? Let me look at that, and then we'll do Lizzie's question next here. Let me put a break in the video so I can remember where to change topics. Let's just take a drink right here, changing topics. Break in video to help Brown with tagging the video later. Let's do this. Okay. Would you care to further explain what details to discuss about leverage in general? Let's Google some leverage. Okay, so we got leverage in here a few times. Task 1. There seems to be task 1, part 5. You got it. I wrote it. I swear. I promise I wrote it. I wrote it on Sunday. My brain's like, wait, what's going on? Last night I was finishing up videos and my brain's fried. Everyone's brain's fried though, so it's all okay. It's all okay. There seems to be an unusual point in the model with high leverage and thus influence. What is the row number for this point and what makes it unusual? Yep. Okay, so we actually have some code for this right now. Let's go grab our model that we made down here, and mine's actually going to have 2, and I'm actually using some code to take that out right here. So when we think about things having high leverage, we need to know this immediately. So if you're listening to this part of this video and you hear high leverage, how would you describe something with high leverage? How would you describe something with high leverage? And this is not your model. I'm just making a similar model or a model that I can utilize. How would you describe something with high leverage? Let me, what is the name of that row? How would you describe, do not make the same model I am making. Someone's going to make this model and the graders are going to be like, what? Something with high leverage is what? I always do that wrong. Oh, I didn't concatenate. There we go. Okay, cool. Kind of. And maybe. Not everything with high leverage is influential. To have influence, things with high leverage have potential influence. To have influence, you must have leverage, and what else? So to have influence, you must have leverage, and you must also have like this point right here, even though it might not look like it has high leverage. Anything with high leverage is beyond this point. So this is high leverage right here, and I have a really good graphic from yesterday. We'll do it again today. But yesterday we drew all over this. So then I'm going to close down. Oh yeah, because I should have it from yesterday. There it is. So high leverage is anything beyond these green lines right here. Yep. And then you also need to have a high deleted studentized residual. So this point right here, do you see this yellow dot right here? This yellow dot, and I'm going to go away. This yellow dot has the most leverage, but it is not influential. You can see it has the most leverage right here. And where is it at in terms of residual and deleted studentized residual? We won't go into detail here, but we will in class talk about what a deleted studentized residual is. Where is it at in terms of residual? And then we'll go into detail in class on a deleted studentized residual. So in terms of residual, just kind of explain, it has a very, very what residual? And it's so funny, yesterday someone said, I thought that was a mark on my screen when they saw it in the lower plot. Its residual is very, very what? It's within the confidence interval, and so it's within what we would, well, that's for the mean of the line. It's very, very small, right? It's very, very small. And down here, when I was zoomed out, someone was like, I thought that was because they saw this right here. They're like, oh, I thought that was a little smudge on my screen right there. But no, that is the point. And that is a point that is basically the model basically predicts this really well. It's got crazy leverage though. But look at the circles as they get bigger as they go down further. They also have to be further out. Like this circle right here is very small. It has a large deleted studentized residual, but it doesn't have enough leverage. Leverage is the further you are away from the mean of the x's. This is where the mean of the x's is, and the further you are away from the mean of the x's, the more leverage you have. What's confusing to people is you have to take this graphic up here and fold it over onto itself. You have to take it and fold it because leverage is the distance from the mean of the x's. So this right here is where you have what leverage is the last thing I'll talk about leverage here. This blue line, since it's the mean of the x's, is where you have what leverage. What leverage do you have at the mean of the x's? If you think about this like a seesaw, just think about this like a seesaw right here. If you think about this as a seesaw, what leverage do you have right there? So what leverage would you have at the middle of the seesaw? And then we're going to use this color scheme to help us in the bottom graphic. So I wish I could do it. I wish I could, like, if you were to take this as a sheet of paper and cut this right here. So here, I'm going to move myself over to it. This might help. Where's my camera? I got to find my camera on the screen here. So I'm gonna cut this right here. I'm going to go. Like, does that make sense? I'm going to cut this right here. And Kayla, you all right? And Roger, you're all right. So does everyone see I'm cutting this right here? I'm like cutting along this. And then I'm going to take this. I'm going to take this. Which one's hand? Okay, good. I'm going to take this and then fold it over like this. Does that make sense? So if I could take this piece of paper right here and fold it over this way, does that make sense? And then look here at this portion of my hands right here. Like this. I'm going to take this. Gosh, it's so weird being mirror image. I'm going to fold it over like this, and that's how we're getting this graphic right here. Do you see where the blue line is at right here? This blue line being right here is because this is now the start of it because I've folded it on top. Do you see these dotted lines right here that would fold over on top of this? Does that make sense? Like these, Oh, yeah, we don't have to get the points to do it. It does it for us down here. This green line right here, I should have made it a dotted green line. But this green line right here, that's not the right color. That green line right there is the same dotted green lines right here because they're going to fold over on top of each other like this. Does that make sense? Like the idea of leverage, like this point over here has high leverage. Oh no, I'm already saying that, Kill. I'm already saying that this is like how Brian's mind works, is he just sees everything in my mind. I'm like the exact opposite. Like there's so many I think you I'm already tell me that, and my mind's very different. It's so interesting how our minds can like do things differently. And to me, I'm just like, I see it like this point right here. If you fold it over to the other side, I'm gonna stop with the example, but I hope is making conceptually, does it make sense conceptually that anything on the mean of the x's would have zero leverage, and that's where zero leverage is, because this is where we have no leverage. So, and actually, I think the graphic technically starts right there. Like that's where zero would be. I guess it wants the circles to expand out, but anything with zero leverage would be at the mean of the x's. And as you go further out, you have more leverage. So going further out you'd go out from both directions. So the bottom points on the bottom model would have the most leverage. With the points down here, which points here have the most leverage? And so only look at the things that apply. Which points here have the most leverage? Like, does this point here have the most leverage? Does that point there have the most leverage? Correct, it does not. This does not have the most leverage right here. This point over here would have the most leverage. This is the most leverage. And the points with the most leverage are the ones just like only looking at leverage. This one would not have the most leverage either. Just the further out you go here, this is just the amount of leverage. So the further the highlighted point does, correct. So leverage is just on this scale. The size of the circle represents the influence, and the influence is a combination of leverage and deleted studentized residual. So you have to have both leverage and deleted studentized residual. Like, why does this point right here not have enough influence? Why does this point right here not have enough influence? Like this point specifically, I'll highlight in a different color. I'll highlight it in blue for the moment. Why does that blue point not have enough influence? What if it's at... Oh, that'd be insane. Oh, wait, point... Yeah, oh, if it was at that, it would be huge. If something were over there, if it had a deleted student rights residual of 4 and it had this, it would probably look something like... It would be like that big. It'd probably be bigger than the other ones. So it'd be really huge if it was over there. It'd be something like this. That's what it'd be. The blue point is missing enough leverage. It would have to go over here. It has enough deleted studentized residual. The model misses it far enough, but it doesn't have enough leverage. So if it were to be over here more, it would then become influential. These are our influential regions right here. Both of these regions right here are the influential regions. So if we move the point further over to the right, it would then become in the influential region. Does that make sense? Yeah, I think, yeah. So that's what we're talking about. Why does this point right here, why does this point I'm shading blue now not have enough? Why is that point not influential? How would we describe a point that is far out? Both, oh, you're looking at the yellow, so yeah. And this one applies to both of these right now. How would you describe a point that is far out? Which point, Roderick? This point right here is far out, but it's not influential because it does not have a high enough deleted studentized residual. So this point right here is far out. It has tons of leverage, which means it's unusual in its X combination, but it does not have enough deleted studentized residual to be considered influential. So the two things you need for influence, are going to be deleted studentized residual and also leverage. So the blue does not have an extreme enough deleted studentized residual. Exactly. The one that has a deleted studentized residual of 4 and leverage of 0.0. Oh, that would be insane. That one would be model breaking. Frankly, the ones that are on here are pretty model breaking. If we had a point over here, it would be so heavily influential. This is going to pull the model towards it. It's going to be something of this size. I'm totally missing on my plot. But this one right here would be super duper influential. It's probably going to be like that size. So the size of the circle is the size of the influence. This would be the most influential point. It might even be bigger than that because it's about as far away as these are. Like this has a deleted studentized residual of about 4. This one has about -6, -4, -6. And this one has twice as much leverage almost. And it's comparable to this. So it's got to be bigger than this one in terms of influence. So this would be crazy right here. This one is like controlling the model, which we don't want. We don't want certain points to have undue influence because think about like in terms of size, this little dot right here has like 1,000th of the impact of this dot right here. Does that make sense? Like when you look at the size of these dots, this is how much it's influencing the model. So that would mean that both x variables wouldn't. So it's not really the x variables; it's the individual rows. So the rows, and we'll look at our data here, and we'll get specific on this. So this point right here, just think about this. This point has about as much influence, probably as all of these points right here. Like, we can actually look at this. We don't need to look at this in our assignment. Cook's distance should be the influence. Yes, and let's go here to max of the Cook's distance, 14. Let's go here to sort. Okay, so here's all the Cook's distances that we have. And did I do it properly? 101. It's giving the row names. It's giving the row names. Okay. And those are very, very tiny. Okay. So if we were to go here to sort, and we were to go here to tail of this, and we were to take just the last one, that's the very most influential point. And now if we go to sum, and I think there's 252. I just want to put this into perspective. And if there's 252, we go 1 through 251. We need to sort it. This is the last. We'll talk about this and then we'll get to the answer. No, let me sort it first. Sort, Cook's, distance. Oh my gosh. Okay, there's the sorted. How many is this? Oh, let's go to length. 250. Okay. And so now we need to go through 1 through 249. And now we want to go here and go to sum. There we go. Wow. Okay. Why do I say wow? When we look at this right here, 1 point has this much influence. This point over here, to put this in perspective, and why influence, which is the size of this circle, is not good. So if high leverage and extreme, exactly, and that's what you're looking at here, high leverage and extreme deleted studentized residual outside of -2 and 2. Okay, that's exactly it. That's the combo that gives something high leverage, and that's why this one's insane right here. But take a look at this. All the points together have an influence of this. The 1 point has an influence of this. What do you think about this? Just think about it like, if I tell you every point, 249 points, have a combined influence on the model of this amount. 1 point has an influence of this amount. So all the points over here together, every other point in the model has an influence of this. One singular point has an influence of this. It's like the sun. Like how influential is the sun in our solar system? Like if Pluto disappeared, it kind of did disappear. It's no longer a planet. Sad times. But how important is Pluto, which is way out here on the edge of the solar system? How important is the sun at the center of the solar system? This is super influential. It has 20 times the influence of all the other points. So in other words, This is basically making our model. Does that make sense? In this instance, and you don't have to go through all these details right here, but the amount of influence this has, it's gonna control the coefficients, Kayla. You're exactly right. It's gonna, because the interpretations are gonna be based on the model. So your understanding of this whole system is literally based on that point. That point is influencing everything. So you're like, if that person had not registered their data, our model would be completely different, which is not good. We don't want our understanding of a set of 250 individuals to be based on one person. So the amount of influence they have is completely absurd. Like, it is just ridiculous. And that's what we're looking at here. So when we look at the idea of leverage, leverage is an unusual combination of the X's. And let's go ahead and look at this individual right here, which this is the main thing you need to do. Like, I'm going to put a cut. This is like the main thing you need to do right here. Like, when you look at something to see if it's unusual, here's what you need to do. You need to look at, your combination of your X's. Let's go here to the pairs. And we're going to write that same code we wrote on like Tuesday or so. I can't even think. So we need to go, we're doing height and weight. You actually don't need the Y variable. I think I included the Y variable last time. You'll have more of these. You don't need, because remember, leverage is only about the X's. You'll have more right here. So you could include like plus another X, but they technically only need to be X's. It's not the end of the world if you include a Y variable. It's just we don't really need to concern ourselves with Y variable. Sure, I'll put in age just to show multivariate. My model doesn't have it right now, but I just want to show the multivariate sense. We're using the body fat data frame, and I did remove these rows because I only want to show the one, like yours will look. Okay, so when we look at this right here, they're pretty easy to identify. I think we can kind of see pretty quickly where this person is at in the multivariate sense. Do you see them? Do you see something that drags away and is super unusual in the multivariate sense? If you look at the cloud of the multivariate X's, you see this right here, which is far away and is going to give extreme leverage. Now remember, leverage, you'd say, but Brian, wait a minute, in the previous plot, they were over on the right. But it doesn't matter if they're on the right or left. This over here means they're away from the mean of the X's, and this is where the mean of the X's is at, 0 leverage. This line right here is not the mean of the X's. This is where high leverage begins. A lot of people confuse this because mean of the X's is when you have no leverage, which is technically right here. Sorry, that's where 0's at. It's usually, anyways. 0 is no leverage, mean of the X's, and then this is high leverage and strong leverage, super high leverage, ridiculous leverage, insane leverage, absolutely, what are you doing leverage, you've gone crazy leverage, oh my gosh, what in the world is this? This is insanity, pure insanity. And you can see it over here in these plots when you look at it and you see it way over here. When you see it way down here, I can tell you that's it, and it's not unusual in this combination. Wow, it's weight and age. I have no idea where it's at in this plot, but I bet it's that, and I bet it's that. Now let's write our code that we wrote. This is the extra little bit. You need to write, I think I can remember it, PCH equals if else, Brian's remembering how to write code, if else, row dot names of body fat contained in the vector, and that's 42, right? Contained in the vector 42, then we will do 8, if not 2. Good, that is it. Yep. Let's go 15. Let me take a look. Work dish, and it didn't work properly. If row dot names, let me run this right here. Where's 42 at? Should come back true. It does come back true. Then I choose divergent enough characters. Let me try with the color. I don't know why I'm not seeing the difference in the code. Maybe it's not that. Color is going to show up pretty quick. We go cull for color, and if else, that should be working. I did it on Monday or Tuesday. Red, black. Did I not include that row? Yeah, let me grab the thank you, Kayla. This is code I wrote. And for some reason the code is not. Let's see what Brian did here. And thank you, Kayla, so much. And this is using the full demand data set. So, oh yeah, because I did the exact. Okay, there's the data. There's the PCH. Might just steal the PCH part of it. So Kayla's helping out real big right there. We got some big help. And there's the if else there. So there's that. And oh, I stored it as unusual. That's all right. It's not like the 42 right here. 42 should work. So, oh, row dot names. Really? Really? Nope, I didn't do it. What is it not like about that? Let's see here. Pairs, body fat. Let's just change this and drop this into here. And then let's go to unusual and let's store into unusual 42. And then let's go to here, drop that, drop that. I really am confused. Oh, there it is. Well, that can't be right. Let me go look at the influence plot again. It must not be that point. I think we figured out the issue, Kayla. It's 41. It's 41. So let's go back in time right here. I'm going to copy this code so I don't lose it. But it's 41, and that would explain what we're seeing. So we've got this code right here. So there we go. Look at that, Kayla. So here is the other code right here, but it was 41. I don't know why, but there it is right there. And yeah, so we can create the data frame. We can do that, and that works a lot if you have like multiple, because I think on Tuesday or so I was doing multiple. And if you go back and probably look at the video, it was probably appearing in this cloud, but I was like, no, it's that point right there. Like, it's that one right there. It has to be. That's the one it is. So I was like, why is the code not working? And I didn't have the right observation. The influence plot confirmed that this is the highly influential point. So yeah, that is, yeah, and there's the extreme leverage right there. And yeah, so this point right here, this person has an extreme, like if we talk about why they are unusual, and we can go grab our CEX, which is character expansion. And we're just going to take this right here and choose a character expansion. And go here to 3, and go here to 0.5. And wow, now they really stand out like a boom. So you can choose different things. You can see this person is not unusual in their combination right here of weight and age. They're actually super common, but their age and their height, they're 26 inches tall and they're about 45, which, I mean, 28, I think they're 28 or so inches tall, which I think the shortest people who have lived are that tall, but also their height and their weight, they are about 200 pounds at 28 inches or so. So they're far away from this. And this is some of the characteristics right here giving them extreme leverage. Does that make sense right here, Kayla? This is their extreme leverage nature. They're not unusual in their weight and age combination. They are unusual in their height and weight combination. They are unusual in their height and age combination. So, and probably a lot of this has to do mostly with their what variable. Like, they are extreme in their combinations, but it also has to do a lot with their what variable that they're extreme in. So this is like how to look at this right here. What variable are they super unusual in? Like in the univariate sense, they're unusual here. In the univariate sense, they're very unusual in this. Then we're going to do the Stato one next. In the univariate sense, they're very unusual in their height. Exactly. And then in the multivariate sense, they're very unusual in their height-weight combination and their height-age combination because they're far away from the density of this cloud. Exactly. They're unusual univariate. Like if you look at the univariate sense, if we just go to a straight histogram of body fat height, you'll see them right over here. So in the univariate sense, they're super unusual because they're very, very far away. So the more we can like join our understandings together of like they're unusual in the univariate sense, they're unusual in the bivariate sense, they're far away from the other x's, they have extreme leverage. Is that making sense? And this is what we need to point out right here. We can also look at like the summary of it. We're only going to look at the start of it. Summary of the first 3 columns, the first 4. And we can see here that their height is the absolute minimal. It'd be hard to see the multivariate sense here. How do you determine that it is a height from the pairs graphic? Good question. So when you look right here, across this row right here is all height. So these are the heights of individuals. So if you go across this individual has a height. They're the same person in all of this, but they have a height right below 30 inches because you're going this way right here. You could also go down looking at height. So if you go down this way, a height of 30 or 28 inches or so is right here. Does that make sense? How when we look at the pairs graphic, if you trace this across, height is on the y-axis. If you trace it down, height is on the x-axis. So this one is a height versus weight graphic where we're looking at as someone's weight increases, their height increases. Not literally in that sense, but 2 individuals who differ by their weight in 1 pound are expected to differ by, but we see the relationship between height and weight, and it's a positive relationship. Does that make sense, Kayla? How we look at across here, weight is on the y-axis, and if you go up and down here, height is on. Exactly. And then when you look at this right here, they're not uncommon. So they're not getting their leverage from this combo exactly. So you can see, and I think this goes to kind of what we were talking about via on Discord, is you can see where they're unusual in their kind of X combinations. And this is only the multivariate or the 2-variable X combination. There could be a 3-variable like multivariate cloud or 4-variable, depending on how many variables you're doing. And outside only with height. Exactly. In the univariate sense, they're odd right here. And we saw that with the histogram. The histogram points out the oddness in the univariate sense, which things that are odd univariate can be odd bivariate pretty quickly. But if they were somehow like, it'd be so hard. They'd have to be way off here to follow the trend. But if they were like way over here, which would be, they're off the graphic then, they could somehow follow the bivariate trend. So something could be odd univariate, like someone who is like, let's say someone is 7 feet tall, but they're 300 pounds. Well, they're very odd univariate, like they're super tall, they're super heavy, but they might be like, short people are going to rule the world. Yeah, all us tall people are gonna like hurt our backs. So it's I think, was it Roger you were saying about your husband, and then because like being 6'3", I'll just tell you my back hurts. Like feet going off the bed, back hurting, just like my back. Just like you ask anyone who's generally over 6 feet, and they'll just be like, my back hurts. So just that's what's gonna take us tall people down. It's our backs. It's not fun. Well, I think it's another student on here is like 6'7", and he's definitely been like, my husband is 6'1". He has, yeah, exactly. I think once you reach 6 feet, your back just goes. Once you reach 6'1", it's like your back. You're like, oh, my back. That's the way it goes. I'm 5'4". Yeah, it's everything has its pros and its cons. And I always want everyone to understand that, like, there's no perfect, there's no normal, there's no, like, that's in statistics. I never want anyone to think we're talking about bad by saying like, oh, this person's very unusual. They are. That's what in statistics we mean unusual. Like unusual can be very good and very bad. Like, unusual, especially if you're unusually tall, you might have an advantage in a lot of sports. I mean, it depends. I mean, it might actually help in wrestling to be shorter. I'd really be interested to see like the best wrestlers. Like if you look at Olympic wrestlers, I'm guessing they're not super tall. So exactly in context, like what is the context and what is the unusual just means far away from the mean. And frankly, unusual are just different. Exactly. And that's what we mean by unusual. Like you're on the edges of, like less frequent observations of this. Like unusual means uncommon. And so, frankly, I wouldn't want to be the mean of everything because then you're the most typical, you're the most common. And you think about like, if you say I got an uncommon Pokemon or something, you're like, oh, what'd you get? And you're like, I got a shiny. Oh, that's super unusual. And so, we're all our own shiny Pokemon. So remember that. Just be like, I like being unusual. I like, having these things that like, I don't know, are not the dominant thing in society. So, as long as it's a good thing, as long as like you're not like doing bad things. Like like I like being a person who robs stores. No, don't do that. That's unusual. That's bad. Don't do that. That's not something to be proud of. That's I don't know. So we have a saying here, you do Mew, but don't go out and break laws. That's not doing Mew. That's not being good. I think there was the question about let's see here. Everybody should read Rumple Buttercup. What is it? By Matt Gray Gubler. It's about how we are all different in that. Yeah, I totally agree, Kayla. I totally agree. And I think that's what's important is we celebrate our differences because that's really, it means a lot to me that I've had a lot of experiences and get to meet a lot of different people in my life because, and for your info, he's the actor who plays Reed on Criminal Minds. Oh, cool. That is really awesome. I didn't know that. That's I think it's just a lot of people here. I'm finding the question. Routine screening. Okay. Yeah, do the routine screening one. A lot of people, I don't know. I think I've been kind of lucky because I think see, there we go. Perfect connections right there. I don't know. You think about, we all have advantages and disadvantages in life. And I think when especially you're a kid, anything that makes you different, like I was ADD, probably still ADD, as you can tell. I remember kids in the 80s being like, you're ADD? Like, what is that? Like, I was like patient zero ADD. Because, I mean, I'm talking like early 80s. Like, I was diagnosed ADD in like 1988. And so people were like, what is ADD? What do you have? And I was like, I can't pay attention. And they're like, why? And they're like, and then everyone started becoming ADD. I was part of the cool kids then. But there we go. We found the one with the routine screening. But I think the hardest thing was, people, when you're a kid, you don't want to feel different. You don't want to feel like everyone, like you're all by yourself, because then you're like, oh, you're different. And you're like, oh, no, I'm just like you. But no, it's okay. It's okay. No one's like anybody. You're you. You're not like others. You have commonalities, but you have differences. And then you can share your differences with people. So, I wish I had understood that earlier on because I think people just are afraid to be different because it's like it's easy for everyone to be the same, but it's better when everyone's different because we get to learn and grow. And yes, anyways, enough life advice with Brian. I know it'd be so boring. I don't like boring. I like interesting. I like mathematics and some people don't, and that's totally fine. Let's see right here. During a routine screening, a doctor notes that 25%, that sounds like a proportion, of her adult patients show higher than normal levels of glucose in their blood, a possible warning sign for diabetes. Hearing this, some medical researchers decided to conduct a large-scale study, hoping to estimate the proportion within 5% with a 99% confidence. I literally sat down and one day decided I'm going to memorize a bunch of Z-scores. You do not need to do that, though. For those who don't like memorizing, because we're all different, we have David M. Lane applet. The David M. Lane applet is where we can go to get Z-scores on the normal curve. So let's go pull up the David M. Lane. Mr. David M. Lane, where you at? Show up, David M. Lane. Ubot, thank you so much. Here is the David M. Lane applet. And what we're going to do is we're going to go to value from an area. We're going to put in 99%. And when we do a confidence interval, we need to shade the middle. And now let's see 99%, and it's 2.5758. So that is the Z-score for 99% confidence. Yours might be different. Use the David M. Lane link in the chat. Now, this is within 5%, and that's going to be the margin of error because they want to do plus or minus that. And this is going to be an estimated p-hat. Are they doing a... Yeah, she's making a confidence interval. This is our estimated p-hat. Once you have p-hat, what do we do immediately? We find q-hat. So q-hat is 1 minus p-hat, so q-hat is 0.75. So we do all this right here. Where is chat? I'm losing my mind. So good deal. So we have here p hat, we have q hat. We are trying to solve for n. And to solve for n, we need to write out our formula, p hat plus or minus a z-score. Then the star is put here because we get to pick it, but the problem did that for us. P hat, Q hat, that's because we're dealing with samples. We do not know the truth. If we knew the truth, these wouldn't have hats, but they do because we don't know the truth. And so now we're going to do some algebra. Life gets easier because we're solving for n if we just solve for n to start before we start plugging in numbers, but we don't need this full formula. We are just solving with the margin of error. The margin of error is everything after the plus or minus. So there's our margin of error. Let's solve. I do not like how my pens keep changing colors. I'm going to reinstall Microsoft Word this weekend. Plans. Margin of error. I hate you, Microsoft Word. Equals z. I do not understand. And we go here, we do square root p hat q hat over n. Now we're going to square it. So let's go right here and square it. So it'll be blue this time, or not. So now, well, that's already squared. This will get squared too. Let's delete those parentheses. We're just undoing the square root, so we have to do that. Now we're going to flip everything. You can do flips in mathematics. So we can just do a flip right here, which is some algebra. So the flip is going to be z over me. And then we do this right here. And we're so close because now we're just going to take and bring p hat and q hat to the other side. So now we get p hat. Sure, why not alternating colors? That's perfectly fine, Microsoft Word, whatever you want. And there we go right there. There we go. Now we're just going to plug in our numbers. We're going to switch colors because why not? And we're going to Space Pen. Going to Space Pen. Let's do it. Ever since Microsoft Word made it so you can't select your own pens, that I've had all these problems. Space Pen, you're not going to be so pretty right there. Let's go Green Pen. Space Pen can be hard to read sometimes. Okay. Don't want people having a hard time reading this. So we're bringing our answer up to here, and we're just going to plug in the numbers. 0.25, these are the numbers we started with. There's the complement of that. So p hat times q hat, the z-score. The z-score was 2.5758. Look at the start of the problem to see how I got these. And the margin of error was 5%, something like that. 5% margin of error. Now be very careful while entering these in. Watch how I do this. Be very careful. A lot of mistakes happen on the entering in of it. I'm going to start with the inside parentheses portion, 2.5758. I'm going to divide by 0.05. Now I'm going to square it. I have now completed this portion right here. I'm going to now multiply by these next two. So we're going to multiply by 0.25, and then we're going to multiply by 0.75. And as long as we didn't misenter anything, 498, because you have to round up on this one. 498. So we'll go right here. We'll delete down, and we will round up. And we'll check answer, and we got it right. It might have some give, though. It usually does, yeah. Usually there's about a plus or minus 2 on these, or this is only a plus or minus 1. So it is a little bit nice, but carry all your decimals and then round up. And that is how we do this one right here. So good stuff. What additional questions are there? I think these off hours go to 12:30. One of these days I'll sleep. One of these days. I slept last night. I think. Really good 320 today. Not too many concepts this week. A little bit easier of a week. Keeps logging out of my Google Calendar. Why does it keep doing that? Yes, that's got it. Great work, everybody. If you have questions, let me know. We did a lot of these questions yesterday, and we actually built 320. We actually built a solver. Do I still have the solver in here? Where's my solver I wrote? Where's my solver? Yeah, here it is. So this is a solver we built for the problems. So 320, we built this yesterday. Prop Z interval. Check this out. So what we do is we built this solver yesterday in about 5-10 minutes. Prop Z interval. And let's go to a question here. So we'll put this, oh no, So we'll go here to prop Z interval. How many successes? So we see right here, they had 136 successes out of 1040. So 136. So we go right here, 136 out of 1040, build 95% confidence. Oh, wait, I totally messed this up. How many successes? 136. What percent confidence? 95% confidence. What was the sample size? This. And there's the interval. There we go. We'll just change the decimals here in a second. But that's got the interval. And round to 1 decimal. There we go right there. And round to 1 decimal. And that's got that. So what this interval means, I am 95% confident the true proportion of people who will respond to the flyers contain the interval. What does it mean to be 95% confident? 95% of random samples will produce confidence rolls that contain the true proportion of people who have the flyer. And we need to have at least 4%. We should do the mass mailing, and we've done it. This is the power of coding. The power of coding. I love it because we have a solver now. So here we go with another one right here. Let's just take our solver. Let's go here with the solver. There we go. We can see it on the screen. Good. How many successes? There are 98 successes. What percent confident? 95% confident. What is the sample size? 536. And that's just a graphical error. We can just ignore that. And there's that. And then there's this. Oh, no. Come on, don't do that. And now we delete the decimals. 1 decimal. Oh, no, no, no. And that's got this. And 1 decimal. We're 95% confident the true proportion of accidents involving teenagers falls in the interval. About 95% of sample sizes of this will produce confidence rolls that contain the true proportion. And the politician claims 20%. Ooh, it's inside the interval because 1 in 5. So this interval does not contradict it because the interval is inside, the figure's inside of there. There we go. So one of the reasons I'm showing this, and we could do this one right here, this one, yep. So we just plug in the numbers and it solves, just to show one more right here. And this is why I like doing code, especially 320, because we can just solve these questions with code pretty quickly. What percent confident? 90% confident. There we go. And there's the interval. So we can use code a lot of times. I wish I could say, like, do you want this returned as a percentage? How many decimals? I could. You know what? Let's do that real quick. So I'm going to update my code to make it like, do you want this returned as a percentage? Do you want it? And then, oh, wait, was that a 3? That is plausible. Yep, there we go. So just looking at one more thing right here. Okay. So with this code right here, I could update it. And this is kind of what we do in 474. At least we talk about how to build functions. I don't know, maybe I'll turn this into a 474 assignment next semester. They'll be like, go check out this video. So when we get the end result right here with the lower and the upper, we could go here to read line. Let's put in another read line. And let's go here to read line. And let's go response. And say, let's go here, read line response. Do you want the answer? Enter Y or N. There we go. I only want someone to enter Y or N. And then we go here. We don't want numeric as dot character, because we're going to take the response in as a character. And then we say, if, do you want to answer as a percentage, right? As a decimal. Okay, yeah. So if response equals yes, then run this code right here. No, wait. If response equals no, because then they don't want it as a decimal. If response equals no, then run inside of here. Upper will be stored as upper times 100, and lower the same. I don't know why I'm copy pasting this. Lower. Okay, good. We'll times it by 100. Let's go right here. And then let's go as dot character. Why not? We can still do that. How many decimals do you want reported? We should do this after. Yeah, sure. How many decimals do you want reported? And response 2. And then we go right here, and we're going to overwrite, and let's put 8 decimals right here. So then we need to go here to upper and lower, and we're just going to run the code, and we want as.numeric for this. And then we run round upper, comma, response 2, store into, and then we'll see if this works. Okay. So now let's rerun the code. I coded way too much. How many successes? We have here 4, 5, 4, 1. What percent confidence? 90% confidence. What sample size? Do you want your answer as a decimal? No. How many decimals do you want reported? I want 2 decimals reported. And let's scroll up. And there it is. We got the graphics error. That's all right. There's the answer on the screen. So we've done it. We've now built this. I need to save this. But with that, everybody, head back here to space. We'll head off. Good work. Keep it up, everyone. You got this. I just want to realize it's April Fool's Day, so I never pulled pranks with 6 years old. My calculus teacher declared that no one would fool him. You got to go fool him. I was 8.5 months pregnant and pranked my... Oh, no. Oh, well, yeah, I mean, can you imagine him being like, no, that's a prank, Kayla? Like, could you imagine if he was like with you pranking him? Like, I mean, that's a pretty good prank. It's a pretty good prank. Could you imagine him being like, nah, you're trying to prank me. I'm not falling for this. And you're like, no, really, I need to go to the hospital. No, really. And he's like, it's April Fool's. It's April Fool's. Well, I guess happy early birthday, not yet, but to one of your kids, happy early birthday. So he was super cool and easygoing. Unfortunately, I've had things happen in classrooms where people have medical issues. Because I mean, when we teach 100+ students, sometimes someone is not feeling well in class. It's happened. I've never had anyone go into labor in class. Never had that. I'm sure teachers have had someone go into labor in class. I mean, it's bound to happen. But if that happened, I'd be like, we're gonna... Do you want us to call an ambulance right now? We'll call an ambulance right now. Oh, I'm sorry to hear that. I hope she feels better. Feel better for your little one right there. So, shout outs to your little one right there. Feel better. But, yeah, could you imagine if your teacher was like, nah, you're trying to mess with me. You're pulling a prank. It's April Fool's. I'm not going to be April Fool's. Oh, craziness. But I really think what's important right here is the whole idea of the power of coding. No, like, I know I'm not like trying to switch topics. I'm going to leave here in a second. But all of this right here, I really like how you can just enter in your answers and you can be like, how many successes? 80. What percent confidence? 99. Sample size 100. Do you want your answer as a decimal? No. How many decimals? 4 decimals. And then it gives you the answer. Yes, to get me warmed up. That's so nice of him. That's awesome. That's the way it should be. Like, you just take it serious. You gotta. The huge risk of like saying April Fool's joke, I'm not falling for it. Don't do it. Don't do it. Don't do it. This is the power of coding. This is what we're teaching Kayla right here. This function, as you saw, I built some more onto it today. I'm gonna save it so I have a function to run around with. But just these little parts, these, as we say, little bits right there. You just build it bit by bit, and you learn how to learn more code, and then you can make it so it gives you the interval. You can say whatever you want. You can go back in here. You can be like, how many successes? 120 out of 400. Oh, well, that's not gonna work. I put in the wrong thing. I could put in some errors, like it could be like, you entered in an invalid thing, and then do you want it as a decimal? No. And then 3. There we go. So it'll turn out. Good stuff. With that, everybody, we'll head off. We'll be back there. I know, I like it. It's, yep, just practicing. It's practice for me, and also it solves all 201 questions for me now. So if I get something wrong, I can double check my answer. I should have it like report the margin of error. I could have it report a list. I mean, it already calculates. It already calculates margin of error up here. There's margin of error being calculated. So it's just doing what I would do by hand. All I did was write out everything I saw by hand and do all the rounding and everything. So it just reports everything back to me. Do you want it as this or this? So I could have put type 1 for percent or type 2 for decimal. Like I could have done that. I just changed right here. That's fine. Yeah. Now it's gonna have the parentheses or the little asterisk or little semicolon. Well, that's got it. Kayla, great job. We'll head off here, head back to space, and we'll leave. Bye for now, everyone. Be teaching soon. Bye bye.